Hello, one and all. Let's go through and identify a whole bunch of solutions as acidic, basic, or neutral. First, a quick recap as to how you can identify acids and bases, because it can seem a little bit overwhelming at times. So if we remember a few important rules, this will help out. With acids are oftentimes colloquially written with a leading H. So notice in all these examples, HCl, HF, HN3, H2CO3, H3PO4, H3C6, H5O7. They all have the hydrogen in front. Oftentimes it's a convention to show that that proton is acidic. Up next, we see molecules with the carboxylic acid functional group. This is arguably one of the most important functional groups in acid-base chemistry. And note that it looks like that. Here we have two examples. We have benzoic acid right here, and we have acetic acid right here. That carboxylic acid functional group, really good at being deprotonated. Anything with a Ka. A Ka is an acid dissociation constant. So if you see something and it has a Ka, that means that you're looking at an acid. Anything with a positive charge that isn't a group 1 metal cation or group 2 metal cations, calcium and below. So in essence, what we're seeing here is anything that is positively charged that's not related to a strong base. More on that in just a moment. And so here we have an example of a whole bunch of things that are. Here we have an example of a whole bunch of things that aren't. We'll build off of this idea in a hot second. With identifying bases, most metal hydroxides are basic. There are a few that are amphoteric, but for the most part, if you have a metal and hydroxide, however many hydroxides you need to counterbalance the charge of the metal cation, you are looking at some sort of base. Like here we have potassium hydroxide, sodium hydroxide, strontium hydroxide, magnesium hydroxide, etc. Ammonia and amines. All right, these are some of the classic examples of weak organic bases. And, well, ammonia itself doesn't have carbon in it. Amine is a classic functional group where we have a nitrogen with a lone pair of electrons on it that's able to accept a proton, act as a base. Just like acids have Ka, bases have their counterpart Kb, a base hydrolysis constant. And remember, if you're trying to relate an acid and a base, a conjugate acid-base pair and their relative strength, you can use the relationship Ka times Kb equals the auto ionization constant of water, Kw. And then finally, anything with a negative charge that isn't the conjugate base of a strong acid can hydrolyze water in aqueous solution. More on that, well, right now. It is absolutely important to know the strong acids. They are HCl, HBr, HI, the friendliest of them. And in the words of John Bon Jovi, whoa, we're 3/7 of the way there. These are the diatomic strong acids, HCl, HBr, HI, just hydrogen and a halogen. Then we have H2SO4, sulfuric acid, HNO3, nitric acid, HClO4, perchloric acid, and HClO3, which is chloric acid. Remember, what makes these things strong is that when they dissociate, when they go in aqueous solution, they go all out. We use a full-headed arrow with them. They make H plus and whatever their conjugate quote-unquote base is. The reason why I say quote-unquote base is because this is a one-way street. This arrow points one direction, which means this Cl minus is not going to be able to react with an H plus to reform HCl. One-way street here. If these anions can't pick up an H plus floating in solution, if they're any way they're going to hydrolyze a bond, they're going to hydrolyze water and break it apart into OH minus and take a proton from it? No, probably not. So if we know the strong acids, the anions that are negligible bases becomes really, really, really straightforward. It's Cl minus, Br minus, I minus, HSO, ClO3 minus, and ClO4 minus. They're all the conjugate bases of strong acids, making them negligible in aqueous solution. In terms of our strong bases are going to be our group 1 metal hydroxides, things like LiOH, KOH, NaOH, CSOH, etc. And our group 2 metal hydroxides, calcium and below. Things like, well, calcium counts as calcium and below, strontium hydroxide, barium hydroxide, etc. So using this rule, we can figure out the cations that are negligible acids. So the cations that are negligible acids are going to be any ones that are related to these strong bases. So for example, Li+, negligible, K+, negligible, Na+, negligible, CS+, negligible, Rb+, negligible, Fr+, negligible, Ca2+, guess what? Negligible, Sr2+, negligibility city, population, Sr2+, barium 2+, etc., etc., etc. The reason why I wanted to emphasize these particular ions is a very good rule of thumb when dealing with salts and dealing with ions in an aqueous solution is if something has a positive charge, in fact, let's back up a slide. If anything has a positive charge that isn't a group 1 metal cation or a group 2 metal cation, calcium and below, it can act as an acid in aqueous solution. Positive charges are good at accepting electrons. Classic example of a Lewis acid. They can oftentimes donate H+, etc. And then anything with a negative charge that isn't Cl-, Br-, I-, NO3-, HSO4-, ClO3-, CrO4-, anything that's not the conjugate base of a strong acid can act as a base in aqueous solution. There are some that are amphoteric, like HS or like HCO3- bicarbonate, for example. But this is a very good rule of thumb to help simplify things and identify especially salts. So now let's go through our identification station. Let's get ready to identify metric crop ton, aka 20. Various chemicals as acidic, basic, or neutral. And the way that I recommend going about doing this is I'm going to take a dramatic pause for about 5 seconds before going through each of these. I suggest you pause and go through and see if you can identify all of these before I go through and classify them. Pause. All right, let's do it. Okay, so we're going to go through and identify each of these things. Here we have a metal and a nonmetal, which means we have a salt. Salts are strong electrolytes. Generally, well, at least the ones that we're looking at in this unit, that can dissociate completely and form their respective ions. So we've got sodium plus and NO3-. So we're starting with a boring one here because Na plus is a group 1 metal cation, so it's neutral. NO3-, well, it is the what of a what, therefore making it what? Conjugate base of a strong acid, therefore making it negligible. Okay, nice try, but this is going to be a neutral solution. All right, up next we have hydrofluoric acid, HF. This is a classic example of a weak acid. So it dissociates into H+ and F-. This is a weak acid. Next we have iron chloride. Iron chloride will dissociate in aqueous solution to form iron 3+ and Cl-. I'm not going to write the aqueous here, and technically it's 3 chlorides here, but for the purpose of identifying as basic or neutral, it doesn't really matter. Now then, Cl- is the what of a what, therefore making it what? That's right, it is the conjugate base of a strong acid, therefore making it negligible. Iron 3+ has a positive 3 charge, and it is not a group 1 metal cation nor a group 2 calcium and below. So this is going to be an acidic solution. Cool. Up next, we have KNO2. How are we going to identify KNO2? So it would split apart into potassium and nitrite, NO2-. K+ is a group 1 metal cation. It's going to be neutral. NO2- looks suspiciously like the conjugate base of a strong acid, but HNO2 is not a strong acid. HNO2 is weak. Because it doesn't have enough oxygens to really polarize the hydrogen bond as much as HNO3 does. Also, it doesn't have as many resonance structures to stabilize the conjugate base. Anyway, NO2 minus, therefore, is going to be a base. This is a weak base. Okay? Negative charge, not the conjugate base of a strong acid. But wait, we've got more. Up next, we have NaBrO3. We have this sodium bromate, which turns into Na plus BrO3 minus. Okay, so Na plus, negligible. BrO3 minus is negative, not the conjugate of a strong acid, so this is basic. All right, up next, we have this amine here. If we draw out the structure, this is what it would look like. Okay, so we have an amine. This is basic. Up next, we have this carboxylic acid here. Carboxylic acids, anything that end in COOH, are going to be acidic. Alrighty. And then finally, we have this down here. This might look strangely familiar, well, similar to something that we've seen before. This is actually an ammonium salt. So an ammonium is what you get when you have a nitrogen with 4 bonds on it, has a positive charge, and this one's just being counterbalanced by a Br minus. Anything with a positive charge that's not a group 1 metal cation nor a group 2 calcium and below is going to be acidic. And essentially all of the ammonium salts that we look at will be acidic. Again, what we have is this nitrogen here. It has a positive formal charge on it. And then the bromide is counterbalancing our organic acid here. Okay. Up next, KOH. How do we identify KOH? Well, got to do the pause. Pause. Beep. Resume. KOH is a strong base. I'm going to dissociate completely. Up next, we have strontium hydroxide, SrOH2. It's a strong base. I'm going to dissociate completely. Up next, we have silver nitrate. This dissociates into Ag plus and NO3 minus. NO3 minus is negligible. Ag plus is acidic. It is a transition metal cation. And finally, we have magnesium hydroxide. Magnesium hydroxide is a weak base. Beryllium and magnesium hydroxide, even though they're group 2 metal cations, they are not below calcium. And so as a result, they're just like, they're smaller. They're able to these ions are able to hug hydroxide more so than like the larger cations like calcium, strontium, barium. So won't dissociate as appreciably as those ones. H2SO4. Hey, we're looking at a strong acid here. LiClO4. It's a salt. It's going to turn into Li plus and ClO4 minus. Li plus, neutral. ClO4 minus, neutral. And this is all neutral. PbBr2, lead bromide. This will turn into Pb2 plus and 2 Br minuses. Br minus is the what, therefore making it what? Good, this is negligible. And Pb2 plus is going to be acidic. Up next, we have this molecule right here. Actually, this one is derived from an example that we looked at just a moment ago. So we have a metal, Na plus. Is the Na plus going to actually influence the pH? Nah. Lol. Okay. And then it's C3H7COO minus. This is a carboxylate. In fact, this is the conjugate base of an acid that we looked at on the previous set here. So negative charge, not the conjugate of a strong acid. This is going to be basic. But wait, there's more. Here we have ammonium chloride. This will dissociate completely into plus and Cl minus neutral, NH4 plus acidic, H3PO4, phosphoric acid, aka this is a weak acid. Cool. Sodium phosphate, it's the conjugate base of the conjugate base of H3PO4. And this dissociates into sodium plus and phosphate, PO4 3 minus. Sodium negligible, phosphate is going to be basic. In fact, this is a very important organic base. Then we have HClO2. HClO2 is an example of a weak acid. Okay? So I wanted to finish by just talking about how we solve for the pH of a solution based on if we're looking at strong stuff, weak stuff, a buffer, or a titration. Let's start with strong stuff. Strong stuff is going to dissociate completely. So for example, if we have HBr, we're going to break it apart completely into H plus and Br minus. So you can use the concentration directly to find the concentration of the H plus in the hydronium here. If we have a strong base, like calcium hydroxide, for example, then we need to be a little bit more judicious with how we do this. It will dissociate completely. Just note, though, that for every 1 calcium hydroxide we have, we're actually getting 2 hydroxides. So in this case, if we had like 1 molar calcium hydroxide, it would be 2 molar hydroxide. Although calcium hydroxide is sparingly soluble, that's a story for a different day, so 1 molar is a little bit excessive, whatever. Okay, weak stuff. Weak stuff. When in doubt, ice it out. We'll do an ICE table. For acids, we can just write them out, dissociating into H plus and their conjugate base. For bases, we always have to react them with water. So like NH3, for example, we would have to react it with H2O liquid, and we would get NH4 plus. In this case, we would always get the conjugate acid here, and hydroxide. Okay, so always write out the reaction. Okay, a buffer. Well, first of all, how can we identify a buffer? So a buffer is going to be when we have a conjugate weak acid and weak base pair. Because the conjugate of a weak acid is a weak base, the conjugate of a weak base is a weak acid. So anytime you see a conjugate acid-base pair together in appreciable concentrations, you want a buffer alert to go off. Buffer, buffer, buffer. Okay. And for buffers, we technically could do an ICE table, but we have a better method. That is the Henderson Hasselbach equation. Which is pH is equal to pKa, the negative log of the Ka of the acid component, plus the log of base over acid. Okay, and then finally we have titrations. Titrations are when we add a strong acid to a base or a strong base to an acid. Or whenever we add a strong thing, be it an acid or a base, to a buffer, because remember, buffers have both an acidic component and a basic component. And these reactions, in essence, they come in 3 exciting flavors. We can have a weak acid, Ka, and titrate in a strong base like hydroxide. It's going to form water. and the conjugate base. Cool. We can have a base and titrate in a strong acid. Doesn't matter what the strong acid is, to form the conjugate acid. Also cool. Or we can have a strong acid and a strong base, and they are going to react with each other to form water. They're going to completely neutralize each other. And for a titration, we're always going to ISF it out. Use an ICF table, because strong things, which is what you have to use in a titration, you have to have at least one strong component, a strong acid or strong base. They react to completion. Remember, ICF tables use moles. So that concludes this little review and gauntlet. I hope that you found this to be useful. And if you find yourself preparing for the acid-base exam, rock it. Or really, if you find yourself preparing for any exam, rock it. Thank you very much for watching. Have a great day.